Hey Matrix, welcome to the next video in the physics playlist. Today we're going to be doing question 7 of the November 2020 past paper. If you don't have the paper, then please pause the video now. There's a link in the description where you can go and download the paper as well as the memo. And once you have the paper, then you can continue with the video. Okay, let's get started with question 7. So question 7 is looking at electrostatics. It says two charged spheres A and B are placed on insulated stands 0.2 meters apart as shown in the diagram below. They've given the charges here as well, so we've got -4 times 10 to the -6 for A and 3 times 10 to the -6 for C. Okay, then we have a test charge M, which is placed here as well. Okay, so M is placed 0.1 meters to the right of B. So 7.1 says calculate the number of electrons in excess on sphere A. Okay, so remember, charge just tells us how many electrons have been added or removed, okay, from a sphere. So let's have a look here. Sphere A says we have a charge of 4 times 10 to the -6 coulombs, okay? And now we need the charge of an electron. So if you remember, the charge of an electron is 1.6 times 10 to the -19 coulombs, okay? So to calculate the number of them, we just divide the charge by the charge of an electron, and we shall get a total of 2.5 times 10 to the to the 23 electrons. Okay, so we don't include our charge or the sign in front of the charge, so we don't include the positive or the negative because we're just taking the quantity of Q. Okay, now 7.2 says calculate the magnitude of the electrostatic force exerted by sphere A on sphere B. Okay, so we're looking for the interaction between these two. Now please remember that charge is a scalar quantity, it's not a vector, so therefore we don't include the charge signs in our calculation. So we don't include the negative and we don't include the positive. We take the absolute value of it to get its magnitude. Okay, so we could say that the formula is actually K times the absolute value of Q1 times the absolute value of Q2 R squared. And if you don't remember, the absolute value of -1 or any number is just the positive version of that number. Okay, so we have the charge. So force of AB is then going to be our constant over here. Okay, that's 9 times 10 to the 9. Okay, then for A we can then say it is 4 times 10 to the -5, and for B we have a charge of 3 times 10 to the -6. Okay, and the distance between the two of them is 0.2 meters squared. Okay, don't forget to square your distance. Right, and if you work that all out, okay, plug that into your calculator, you should get a value of 2.7 newtons. Now, yes, we have calculated a force, okay, so we do need to indicate a direction. Now remember, positive attracts a negative, so this system is going to move, or A will move to the right if there's an attraction, or we can say that B moves to the left. But because the question says the electrostatic force exerted by sphere A on B, okay, so we're looking at how does A affect B. B will move to the left. Okay, now 7.3 is a definition for electric field, so you guys can go and look up your definitions for electric field, and you can write out that word for word. Okay, so I'm going to move to 7.4. It says calculate the magnitude of the electric field at point M. Okay, now please remember, I've stated it here, the electric field is a vector. Okay, so therefore we need to pick a direction. Okay, so what I'm going to do is I'm going to take right as positive and left as negative. Okay, once again, we do not include the sign in front of the charges when we do our calculations. Okay, if you want to include a negative or a positive, then put it in front of the E. Okay, So there's our formula for electric field. So for A with respect, or M due to A, so E of AM, okay, we can see that it's a negative. Also remember, our test charge is always positive, so they will attract each other. Okay, so which means M should be moving to the left. So I'm going to put that as a negative there. Okay, which is then our constant again, 9 times 10 to the 9. Okay, the charge of it is 4 times 10 to the negative 6. Okay, coulombs, all over the distance from it. Now remember, it's 0.2 plus 0.1. Okay, and that's all squared, and that should give you an answer of 4.0 times 10 to the 5 newtons per coulomb, negative 1. Okay, and now because this was negative EAM, you can take the negative over, so technically EAM will then equal to negative 4.0 times 10 to the 5 newtons per coulomb, negative 1. Okay, now we can do it for B and M. Okay, so because B is positive and M is positive, it's going to push M to the right, so M's moving in the positive direction. So positive electric field, B, M, which is then going to be again K QB over R squared. So plug in all your numbers. Okay, then the charge here was 3 times 10 to the negative 6 coulombs. Okay, and that is all over the distance, 0.1 squared. Okay, and if you work that out, you should get a total of 2.3 times 10 to the 6 newtons. Okay, but remember it was positive EBM, so this stays positive. Okay, now all we have to do is take the net electric field, so we sum everything up, so E net is going to equal to E of AM plus E of BM. Okay, we said that AM was negative, so it's negative 4.0 times 10 to the 5 minus 2.3, plus 2.3 times 10 to the 6, which should give you a final answer. Oh, sorry, I made a mistake up here. This should be 2.7. Reading my notes wrong. Okay, so that's 2.7, and now this answer here should then be 2.3 times 10 to the 6 newtons, and because it's positive, it's to the right. Okay, moving on to 7.5. Okay, so now what's happened is we've introduced another charge D above A. Okay, and they've given us the resultant force due to putting this in, and they've given us the distance. Okay, so there's a few ways we can go about doing the following questions. I'm going to show you the simplest way, but let's look at 7.5. So 7.5 says, is the charge on D positive or negative? Now note that before we had D, okay, A was being attracted to B, so it was just moving across horizontally. Okay, so the resultant vector was then to the right. Okay, but now we've added in D, and we can see that the resultant vector is no longer sitting flat, but it's now sitting at an angle, which means that D must be pulling A, which means if D is pulling A or attracting A, D needs to be positive. Okay, now 7.6 says calculate the magnitude of the charge on sphere D. Okay, so once again we have our resultant vector. So our resultant vector due to B and D, okay, that's A, they've given that is 7.69 newtons. Okay, so if we shift this across, we can make a right angled triangle, and we can use Pythagorean theorem. So if I redraw this, I'm going to have my resultant vector FR. Okay, remember head to tail, that's FB Okay, and then this here now becomes f of a d. Okay, so I have my 90 degree, so I can use Pythagorean theorem. I have the hypotenuse and I have the base, so I can calculate the height. So f of r squared is going to equal to fab squared plus FAD squared. Okay, so we're looking for FAD. We have this over here, so we have 7.69 newtons squared equals to this one squared, which was given in 7.2. So if you check back in 7.2, it's 2.7 newtons squared plus FAD squared. Okay, so if we sort all this out, okay, we're going to minus this from that, okay, and then square root everything, and you should get an answer of FAD equals to 7.2 newtons. Okay, and that's how we go about doing this question. Okay, if you found today's video helpful, then please leave a thumbs up on the video. It does help a lot. If you have any queries regarding this question, then please leave them in the comment section down below and I'll get back to them as soon as I can. Please go check out the channel. There's maths videos, chemistry videos as well. While you're there, please consider subscribing to the channel. It also helps out. And thank you for watching.